Let's continue. And the next speaker today now is Sahil Joshi, and the title of his talk is Determinants of Twisted Generalized Hybrid Waving Knot. You can start, please.
Okay, thank you so much. Okay, sir. Shall I begin? Yeah.
Yes, you can start.
Okay. So good evening, everyone. So firstly, I thank the organizers for this kind invitation of the talk. So in this talk, I shall be discussing about this family of knots, which is twisted generalized hybrid weaving knots. So I shall be talking about mainly about their determinants. So this is a joint work with my research advisor, Madhiti Prabhakar. So let us begin. So what are they? So we take three positive integers m1, m2, and n and an integer l. So this twisted generalized hybrid weaving knot is denoted by a Q3 at, and with these parameters m1, m2, n and l, and it is the closure of the three-strand braid. So where the braid word is the following. So it is sigma 1 power m1, sigma 2 inverse power m2, the whole raised to power n, and this sigma 1, sigma 2 raised to power 3l is actually a positive twist if L is positive of the entire braid. So if L is negative, then it will be a negative twist, full twist when L is plus or minus 1. And so on, L can be any integer. So this family is a generalization of the classical weaving knots on three strands. So if we substitute m1 equal to m2 equal to 1 and L to be 0, then we get the classical weaving knots. And this is also a generalization of hybrid weaving knots if I substitute m1 equal to m2 equal to m. So this family was defined by Singh and there were other authors, and this is defined by Singh and Chbili. So they mainly studied the colored HOMFLYPT polynomials of these knots. So here is a diagram of a knot. So sigma 1 is repeated m1 times, sigma 2 inverse is repeated m2 times. This entire pattern is repeated n times. And then there is full twist of the braid L times. So this is a typical diagram, knot diagram. So here are some examples. So this trefoil knot is actually one of the examples. This 4-1 is another example. This is a weaving knot. And if I take the same braid and give it a negative twist once, so we obtain the knot 5-2. And if I consider this knot corresponding to these values 3, 1, 2, and 0. So we obtain by taking its closure, we obtain the 8-5 knot. So this family contains a lot of knots which are already known to us. So another interesting family is of the quasi alternating links. So it is the smallest set of links which satisfy the following property. So the trivial knot is in this family, and this family is closed in the following sense. So if I take any link L, which has a projection with a crossing, such that if I resolve that link at this crossing, both its resolutions are in Q, their determinants are positive, and the determinant of the L is the sum of the determinants of its resolutions, then L should be in Q. So this is another interesting family. So I'm denoting this family of twisted generalized hybrid weaving knots by F, and Q is the set of quasi alternating knots and links. So there are some knots which fall in Q, which fall in this category also. So here are some facts about these knots. So every alternating knot is already a quasi alternating knot, and all the quasi alternating three braid knots and links have been classified by Baldwin in this paper. So this is a part of one of the classification theorem, that if I consider this knot, this twisted generalized hybrid weaving knot with these parameters, so it will be quasi alternating if and only if L takes the following three values, plus, minus 1, and 0. So due to this fact, if I take M to be 5, then we get the knot 820, which is of course in this family F, and it is a quasi alternating knot, and it is a non-alternating knot also. If I take M2 equal to 3 and L2 be 2, then we get this knot 10, 139. And the purpose pair is obtained if I take 5 instead of 3. So these are, of course, twisted generalized hybrid weaving knots, but they are not quasi-alternating knots because of this classification theorem. So these are some examples. So let me go ahead. So I am interested in the knot determinant of the knots in the family F. So determinant of a link is defined as the absolute value of the matrix V plus V transpose, where V is a Seifert matrix for L. So which comes from the Seifert surface. So we all know this. But alternatively, this can be defined as the absolute value of the Alexander polynomial evaluated at -1. So I shall be evaluating this quantity to find the determinant. And here is some importance that why studying knot determinant is important. So it is important because it solves the problem of colorability of a knot. So for any odd prime P, we know that the knot is P colorable if and only if P divides the determinant of the knot. And there are some interesting conjectures, like for any quasi-alternating link, its crossing number is less than equal to the determinant of L. So this conjecture is still open. And there is another conjecture, which is the volume determinant conjecture, that for any alternating hyperbolic link K, its hyperbolic volume is less than 2 pi times the log of the determinant of that value. So if we can evaluate the determinant for some families, then we can test these conjectures on these families. So our aim is to find the determinant of this quasi-twisted generalized hybrid weaving knots. So before going to the result, I will just describe briefly what are Lucas numbers. So they appear in the result. So for any positive integer m, so Lucas numbers is a sequence of numbers which is defined by the following recursive manner. So first entry is 2, second entry is m, and the n plus 1th entry is by taking the following sum of the previous 2 entries, right? So this has a nice formula, like just like the Fibonacci Binet formula for Fibonacci numbers. So M Lucas numbers have a Binet formula, which was proved by Falcon in 2011 in one of his papers. So this formula says that if I take this ratio phi m to be m plus a square root of m square plus 4 by 2, and then the Lucas numbers can be given in this form. So if I substitute m equal to 1, then we get the golden ratio, and m equal to 1 case corresponds to the classical Lucas numbers. So very late back, Oesper in 2005, she proved a determinant formula for the weaving knot. So this is already known in terms of the Fibonacci numbers. So Cj is the alternating sum of the first j Fibonacci numbers. Then the determinant can be given by this formula. Later, Kim, Stees, and Talman in 2016 found a reduction of this formula and showed that the determinant can be written as Lucas number 2n minus 2. So in a parallel work, we also obtained the same result by studying the Jones polynomial of the weaving knot of type 3, n. And later we came to know that these two formulas are already available for the determinant. So we will prove this formula also by using our main result. So let us move forward. So Singh and Chbili in the same paper where they have defined these twisted generalized hybrid weaving knots, conjectured that the determinant of hybrid weaving knots and certain twisted hybrid weaving knots can be expressed in terms of these generalized Lucas numbers. So this is their conjecture. So it is the hybrid weaving knot, and this is the hybrid weaving knot with a positive twist and a negative twist. So it is given that this determinant turns out to be in terms of the Lucas numbers. So let us move to the result. So this Artin braid group 3 it can be finitely presented in the following manner. So, and its reduced Burrow representation is the following, where so the generator sigma 1 is mapped to this matrix and sigma 2 is mapped to this matrix. So this is a theorem from the Birmans' monograph. So this is for general Artin braid group Bn, but I am writing it for n equal to 3. So because our knots which we have considered are on 3 strands. So if beta is any braid such that its closure, if we want to give the Alexander polynomial of the closure, so it has a nice relation with the image of the braid word beta. So this is the following relation that it turns out to be the determinant of this matrix minus the identity matrix. So I want to evaluate this thing at t equal to -1 to find the determinant of the closure of beta. So for that, I will evaluate this quantity on the right side. So this is our main result, that for any twisted generalized hybrid weaving knots, the knot determinant can be given by this formula. So this formula, it seems a bit complicated, but it is very simple. It turns out to be in an eigenvalue of some matrix. So here is an outline of the proof. So we can apply the Berman's result. So suppose phi is the group homomorphism of the reduced Burrow representation. And let me set A to be the matrix phi of sigma 1, which will be by substituting t equal to -1 in this formula. So, and similarly, matrix P. So now for the braid word beta, if I take it to be the following, then its closure will be the knot which we have considered. So I want to evaluate this matrix at t equal to -1. So by using the homomorphism property, we can get this, that this will be equal to a raised to power m1, b raised to power -m2, and so on. So we can observe that AB product of the matrix AB and its cube is actually equal to negative of the identity matrix. So if I put my matrix C to be the following, then we can multiply these two matrices. So A power M1 will be, M1 will appear here in this entry. So similarly, we can get this. So this is a nice matrix. It has distinct eigenvalues, which are written here. So it is a diagonalizable matrix. So I want to find the powers of this matrix C. So for that, we can use the, because the fact that this is diagonalizable. So then the determinant of the knots we have considered is just the modulus of the this value. So let me show the final calculation. So by the Berman's result, if I substitute t equal to -1 in that equation, I get the following. And here I have substituted C for this matrix, and this simplification can be done. And finally, this will be the determinant of this diagonal matrix plus -1 raised to L plus 1 times the identity matrix. So this determinant can be written as a product of the diagonal entries. So this is the final determinant. So since their product is -1, so +1 we will get by multiplying these two quantities, and +1 we will get by multiplying these two quantities. Therefore, there is a 2 coming, and this is just the multiplication of these two entries. So if we take the modulus, then we get the required result. So now we can see some applications of this result. Like there is already a proof for this determinant formula for the weaving knots, but we can give a very simple proof of the same. So if I substitute M1 equal to M2 equal to 1 and L to be 0 in the main result, the equation, which is the main equation, it reduced, which is, let me just go back. So this is the only equation in this paper. So which is labeled. So this equation, it reduces to the following. And this quantity is just the square of the golden ratio. So we can get this formula, Lucas number 2 and -2. Moreover, we can give a proof of the conjecture of Singh and Chbili. So this is the conjecture. So if I substitute M1 equal to M2 equal to M in 1 and phi M for this value, then we get that the determinant of this knot is equal to this expression. And this turns out to be the square of that ratio phi, that number phi. So we can, and this is equal to the mth Lucas number, the 2nth Lucas number corresponding to the M. And if by substituting L equal to 0 and +-1, we can get these two formulas. So apart from this, we can also recover the determinant for the torus knots just by substituting M1 equal to Q, M2 1, N1 and L to be 0. So then the equation 1 yields the formula for the determinant of the torus knots and links. for of type 2, q. Moreover, we can consider this subfamily from the F, and if I substitute these values, then we get again this determinant in terms of the Lucas numbers. So this can be achieved by substituting M1 equal to 1, M2 be 5, and NLNR. So why this is interesting? If I substitute N equal to 1 and L equal to 2, then I get the Perkos pair in this family. So whose determinant can be given by this formula. So it is already known that what is the determinant of the Perkos pair. So this is a table which shows that the determinant for these twisted generalized hybrid weaving knots can be given by using the formula which we have obtained. So these knots which are marked in red are non-alternating knots, and this 10, 139 and the Perkos pair, they are not quasi-alternating knots. So their determinant can also be given by this formula. So moreover, there might be many knots which fall in this family. Their determinant can be given by the formula we have shown. So these are the corresponding values for which we can obtain these knots. And these are the references, some of the references. And thank you so much for